Hello, everybody. So tonight is one of the big topics for this level class, kind of taking programming a step further. Thinking ahead and planning about what we're going to do. We're getting started into that data structures. Short version of it, databases or storage long term, but we need to get our data from there into RAM, processed, and back out of RAM in the best way we can, the most efficient way possible, the best way for the particular program we're doing. So there's lots of different ways we can organize that. We're going to start talking about that tonight. And that's pretty much like 4 days of lecture, drawing pictures on the boards, things we're not actually going to make in class, talk about the differences between stacks and queues and linked lists and different types of trees and hash tables and a whole bunch of things to talk about. So I also planned on breaking that up a little. So like what I have on the notes for tonight is we'll start talking about data structures and probably look at linked lists and maybe talk about stacks and queues. We'll make a simple one at some point. Might even do that tonight to see why we would do this. The examples in the textbook show like a completely generic stack. Like it is just, it's a class to use with only the element for a stack, and that's not how we would actually use data structures in our stuff. Then we'll probably go and then we'll talk about stuff because and then the list for tonight, I was also thinking about maybe jumping in and doing the CI/CD pipeline or Docker image. Not sure how much we're going to do that, and I just thought I might start with an example, and then we'll do some lecture stuff so we can see where this is building to. Because when we do the examples for the next couple of days, well, the textbook, all the examples there are very generic. They stripped it down, and their example of a stack is only a stack. It's kind of a stack that's used like an array, and that's built into our language. We don't need to recreate an empty stack. So maybe I'll do it with linked list real quick. Let me clear up on my screen. Yep, I did have it. I believe all of you all know I'm in grad school right now for mathematics, and in my applied linear algebra course, 600 level course, there is a programming project, and that was open on my screen. So I thought I should check and make sure that wasn't open before sharing the screen because 600 level course has much messier, much more threatening looking code than a 200 level course. Y'all don't need to look at code like that. So let me share the screen now that I've blanked out NetBeans again. I'm going to do a quick little introduction this way. Usually I do this later, and I have something in mind for next week. I'll just do it as a Java application, create a new Java application. Sure, this probably is fairly worth saving. This is our introduction to things. So y'all remember when we were talking about object-oriented stuff, we built those animal classes? I'm gonna jump over in GitHub and download the animal class. Here's our thing. This one. The first version of this, I might have to go back to an earlier version. Oh, that's the abstract version. Let's see, history. It was like this very first one was the one I want. See the file. Yeah, there it is. I don't know why GitHub used to let us download the earlier versions, but now all we can do is copy. I'm gonna make it a Java class, call it animal. This time I'm gonna call it animals instead of animal. Because remember we made that, well, I guess open my GitHub here. We made this animal class, and each one of our animals had those specific traits of it. But usually when we're processing data, we're gonna have a whole bunch of things, right? We're gonna have a whole bunch of animals in our data set to work with. So what we've seen so far is we could go over to our main method and create an array of them. But, or a linked list. That's what we're getting anyway. We saw a linked list, so we could go over to the main thing and create a linked list of animals. But if I paste all this stuff in, which GitHub used, oops. Why does it not let me copy that? I'll do this. Might as well show this. So let me go back to the code, get off the history page, copy this, and come down to like my delete folder. Open up PowerShell here, and just say git clone that thing. And we do git log one line. Whoops. Sorry. Change directory into that repository, which, by the way, the repository is the folder. The website is not a repository. The website is just a server holding repositories. The folder itself is the version controlled repository. So now I can just pull up the log of everything we've done here and say way back here was our initial object example. So I copy that ID here and say git check out that earlier version. Well, it's not the folders. See, we're back to seeing the earlier version now. So now I can go over here and open this with Sublime and just copy that file over. So under critters, source code, critters. Here's our original animal object. Sorry, that was a lot to copy and paste, but there's the version control stuff, right? GitHub is showing the most recent version where we made a whole bunch of changes. It's like, no, I want a way earlier version. So we can just, it's version control. We have control over it. There's not much hidden in the name, version control. What's that one? What's that? Close that. So now I can paste that in. Well, I copied it from the other package name, so I need to click the light bulb and change package strict, change to the correct the package declaration. And I want to call this animals instead of animal, which I should right click, refactor, and rename. What? I'm trying to change it the other way. Rename. There we go. I don't know what it was doing. It was only suggesting that I change the file name instead of change the class name to match the file. But I'm gonna change it from animal to animals, because usually we're gonna have a whole lot. And I mentioned earlier, we probably come over here, what we've seen so far, and we make one of those generic linked lists full of animals, right? And dot, dot, dot. We do all the stuff we've seen so far, no surprises there. Add all our things to it, but we use that generic linked list that comes with the language, the catch-all version, the one that has to be prepared for any situation we throw at it, which means a lot of overhead. There's a lot of stuff in that linked list that, and it is very, very unlikely that we would need all of that functionality in any one particular piece of software. That's where data structures come in. So a linked list is actually one of the easiest to make. I'm going to make a new animals object and call it next. Now this is a linked list. That's all it is. One more variable, just a pointer at the next animal. So we probably want a couple other things. So like iterate through. I'll come down here and add a public method. Iterate and print. Maybe all we want to do is print out all of our animals. So you're taking an animal object, and typically we call it head. The start of the list is the head. And while head.next is not null, we won't even pass it in. We'll just start at the beginning of the list, and we'll say an animals object called head current is this object, the object we're starting on. And while current.next is not empty, we'll say current equals current.next. Actually, make this public so that that's accessible, so we can actually access. So we have this public variable called next, and as long as the next one's not empty, we'll just go to that, and I'll just print out all of the things along the way. Print out this .toString. Oh, whoops. Public void. So one data field, and then this list to iterate through. So we just have a pointer that goes to the next thing, and however many next we have, we'll just keep pointing until we get to it. Maybe one more method, public void add, and we'll take in an animals object, call it A, and animals.current is this object, and while current.next is not empty, current is current.next. So we will just traverse all the way. I have no idea why I typed that. Animals, then space current. And then we will traverse all the way through those pointers. Is the next one empty? No, next, I don't know. And when we get all the way to the end, right, when we see a null at the end, that means we're at the end of the list. So at that point, we'll add this. At that point, current.next is that animal object we passed in. Maybe for clarity, I'll call it new animal. So after we go through all of those pointers, when we hit a null one, we'll just add another one here. So that gives us a way to add things to the list and then print them all out. And notice how we don't have any extra overhead for that. The two things we want to do. We want to add to the list and then print them out. And that's all we are loading into RAM. We don't have any extra. That's how easy it is to make a linked list. And notice how I just did it in the object. Took that animal object and one data field turned that into a linked list. And then we just add in the methods that we want for that linked list. That's the sort of stuff we're talking about in next week. So most of our examples are going to be very generic. So let's make animals. I'll call it list of animals is a new animals. And really when we start the list, we want the first one. So our constructor was, what do we have? A name, age, and weight. I'll use that one. A new animal, and maybe we have Fido, who's 3 years old and weighs, I don't know, 88 pounds, like a Malamute or something. 88 pounds is a pretty big dog, I think. Oh, I forgot new animals. And then to get more, we can say list of animals dot add a new animal. We'll call it a new animals, call it Fluffy. Maybe that's a kitten. So like 1 year old and weighs 4 pounds. I have no idea how much kittens weigh. Copy that. Paste Spike, who's 12 years old and weighs 43 pounds, something like that. Iterate and print. And we get our print statements. Oh, it just kept printing the same one, didn't it? I have no idea what was running there. What did I miss? So we start on the current one. Next is not null. Oh, yeah. Start on the current one, which should be null, and then we'll add another one. So I'm going to add some echoes to see what it did. Moving along. And then added it. Let's see if that worked. Added it. So we have the first one, and then added two. So they should be in the list. So it must have been somewhere I printed it. So we start with the current one. If next is not null, we print it, and then go to the next, and then we come back around. That should happen 3 times, right? Sorry, I do not see a typo that I made here. Oh, I need to initialize this next equals null. Maybe that's not actually initializing to null. Yeah, it is. I mean, this is going to look strange, but I think this will quickly fix this. animals current, I'll pass it in. Nope, that's gonna make it complicated. Okay, I made a typo there somewhere. We'll get back to like little errors. Why did this one work and not that one? So take these echoes out. Oh, whoops. That's what I did. I don't want to print this to string. I want to print the current one to string. Sorry. So with that typo fix, now if we run it, there we go, we get our list. Or I could check this if current is not null. That way we actually get the third one. There we go. Because the third one, the next is null, right? So we weren't actually getting there for the third one. Little things like that to think about. But see how our list, we now have a linked list, but there's no extra overhead at all. The only functionality we have is the only things we're loading into RAM are the exact things that we want to do. Why does Spring Boot keep running? Zoom stuff's in my way, and I can't see the buttons. Oh, it's not running. Okay. I don't know why Spring Boot kept running, but that's sort of the idea of data structures. Usually I work this in later, so I'm showing that first where we're getting to. Next Thursday, I was going to do an example where after we've talked about some data structures, we'll do something like a payroll. Because when we do a payroll calculator, right, up to this point, you've made the calculator and then you keep doing more and more inputs. Normally in a real situation, if we're going to do a payroll, we're going to do payroll for every employee. So really, we would want to have some sort of list for that. My plan for that one is have a stack, and then we'll go through all of the employees every single time. So we don't need the individual ones, and we'll make it a stack so that as soon as we process a particular employee, it comes out of memory. In this case, it's still in memory, but that's the idea. We'll try looking at it first instead of last. So now instead of a class to store our data, we have a linked list. We have a custom-made linked list that is perfect for our software instead of that generic catch-all one that comes with the programming language. Okay, so now to the board, there's going to be lots and lots of talking. Basically, the next 4 days are all talking and pictures on the board. And the examples are going to be small, so we're going to break it up. We'll talk about data structures for a while, and then I have some other things, and we'll look at some stuff with JSP pages. We're going to look at CI/CD pipelines and Docker. And I said that backwards because our continuous integration, continuous deployment. We'll talk about it in detail when we get to it, but that's what replaced versioning. Like that old version 4, release 3, patch 17. Instead of those 3 numbers, they can be dangerous from the software developer's perspective. We want control over that. So the modern way is what the end user actually gets is just a URL to the repository. And they always get the latest version from the main branch of the repository. And then we don't have to worry about the version number. And from the user's perspective, they just double click on an icon like they always have. But we don't have to worry about them messing up configuration files or deleting the images that would go on our buttons, or we don't relinquish as much control to the user where they can break our software. But continuous integration, continuous deployment, we'll see that just to break away from the lectures, and then some other examples, because it's an immensely useful thing. Probably seems somewhat confusing until you've done it a few times and got some experience with it. But we'll just kind of introduce it here. That's the notes for the next section. We're gonna talk about a few data structures, and we're also gonna look at a whole bunch of ones that are built into the Java language. So data structures. The next big topic new for this course. I remember why I had the paper in my hand because I had the technical definition wrote down. Organizational and management methods for processing data. Something along the lines of that. It's how we organize and manage the data for processing in RAM. In layman's term, we could say that how we get our data into RAM, processed, and cleaned up afterwards. And there are a lot of these. There are lots and lots and lots of them, and there's not a one size fits all. As you progress as programmers, one of the things that experience adds up for a lot is over the years you'll figure out which data structures are better for a given situation. And it's not always the same. So like next week, probably around Thursday, we'll do an example where we're actually applying data structures in situ, and we'll do a payroll thing with a stack where we have a CSV of everybody's pay rates and names, like from a database. We'll just kind of abbreviate it and jump right to the database, export it a CSV file and read from that. Then we'll have like everybody's hours that they work in a file, and then we'll just have a list, kind of like we just saw with animals, like a list, only it's going to be a stack, so that as we go through and process everybody's payroll, we also remove it from RAM afterwards so that other software can use it. Remember, RAM efficiency isn't just for us. Right? I'm sure everybody's seen it before, but if I come over to a Windows machine, I'm on a Windows machine, so I have Windows X, open Task Manager. Right? There's all of these applications running. Google Chrome I shut down, but it's still doing stuff. But the applications aren't the only things running. We also have services in the background. So we also have all of these things running. So if our software starts to eat up RAM, it's going to mess with other stuff on the computer. So it's not just our software that needs to be efficient, it has to be efficient in order to work with other stuff. Because if people quickly notice that if every time they run our software, other things on their computer start slowing down, right? Every time they run our software, the YouTube video playing classical music in the background starts to slow down and glitch out. People are going to notice that pretty quick and stop running our software, right? So we do have to worry about it, even though RAM is huge anymore. We can still burn through all of it. I think everybody that plays games knows that, right? Every gamer knows our RAM chips might be massive, but we can still burn them up pretty quickly. We can still grind things to a halt. Linked list is a good starting point. So let's talk about what that is. It's actually the one we already started on. So I'm gonna draw a bunch of stack heap diagrams here. Which stacks and heaps are data structures. We will see both of them this week. We'll see stacks tonight. We'll talk about heaps on Thursday. I'm not going to have you make a heap, but there is an example in your textbook where they make a heap. So stack is the last in, first out structure. That's where we put our code. Y'all have all seen these. I use these pictures all the time. So we create a variable over in our code. I'm going to call it list. And what that has in Java, that actually goes to a hash table. Might as well draw it accurately this time. So there's a hash table. And over on the key side of our hash table, they're too small to see keys and value. So we have this hash. We're right a little bit bigger. I am a long way from that. So that variable points at a hash table. And a hash table involves keys and values. So we'll run the list through a fancy algorithm. We'll talk about hashes Thursday. We'll run it through a fancy thing, but then we'll get a number. I don't know, 1, 2, 3, 4. Obviously, a much bigger number. You all have seen that. Whenever we print things out that don't have a 2-string method, we get an 8-bit hexadecimal number. We get one of those. And that is the key to an integer. So say 109. And then that is the spot in memory where we start. So way over here, I guess near the beginning of our RAM chip is bit 109. And that's where our first data point starts. All the bits that make up it. And then we just add a little bit extra on. And this is that next variable that we threw in there. That data field that points at another one. So it can point over here. Maybe there's another one down here. Have all the bits making it up. And then we have that next. Again, I'll point one more over here. Get our variable, and then eventually we get to one that just points at nothing. Internally on the machine, that electricity just flows to ground because there's not anything left in that chain. So we would call that null terminated. Am I still on the video? Yes. So our list is null terminated whenever. You'll have probably seen null pointer exceptions as problems, but in this case, a null pointer is a good thing because that's how we rely on that to know when we get to the end of the list. It's not an error here. It's actually something our list depends on. Lists are nice and dynamic. Y'all have probably seen lists with, I'm quite sure I've drawn this picture before. If we want to get rid of this one, we could just point at this one instead. We saw 2, and you notice that, hopefully you already noticed that pattern in there, like while current is null or current.next is null, or before long, at some point, we're going to go to current.next is null. But we have a loop that we just loop through until we hit that null pointer. It's really easy to add a counter in there, and that's where your indexes go. Start a counter at 0, and then while current is not null, current equals current.next and counter ++, and then go until you match that index parameter that you passed in. Really easy to build just the functionality we need. But that's the idea of a list, is everything just has a pointer to the next element. It's dynamic, so if we wanted to add more, we just add something here at the end of at the last element. We add another one. And now this one has the null pointer. If we wanted to remove something, we just stop pointing at it. And that was our example, seeing how those kind of went in. 2 very important ones. One of them is in this picture here. A stack is sort of the way a computer naturally processes things. Yeah, I'll erase this. A stack, first in, first out collection. That, and that's basically the definition. The important part is out. With linked lists and arrays that we've seen, we keep the data in there, right? We load it in and then it stays there. A stack, we actually remove it. Right behind that is a queue. A queue is a last in, first out. I said that backwards. Sorry. Stack is last in, first out. And a queue is first in, first out. Sorry, y'all have probably heard the word stack before. Nobody called me out. Stacks are kind of the way computers naturally want to operate. Queues would be the way that a human wants to operate. So stack, the last thing we put in there is the first one comes out. Dishes, plates in a cabinet are a standard example, right? After washing the plates, we put them up, and then when it comes to meal time again, we don't pull a plate from the middle of the pile. We usually grab the plate off the top. A queue would be like a line at McDonald's. The guy to McDonald's, the first person to get there is first person to place the order and get their food. It goes in order. Those are probably the two most common first in, first out collection of data. And again, the big important part is this out. So they automatically clean up after themselves when they're done. Yeah, so I guess we could kind of look at some of these, just some generic examples of what they look like. We can make them. We will probably make one at some point. I'm thinking next Tuesday we'll do some simple things, make like a very generic stack and a very generic queue out of a linked list. If not, then the next Thursday when we actually get to that payroll example I talked about, it's going to be a stack made out of a linked list. So we'll see how to apply them there. But for now, we have just some generic reference to them, and most anyone that we could name is built into Java. If this was a computer science class, we would have to spend a whole bunch of time learning how to build them from scratch, even though they're already in basically every programming language we can name. But this is software development, not computer science. We're not looking at we just want to make it work. So we'll use the ones in the programming language. So in Java, there are two fundamental types. In Java, two fundamental. Types of data structures. One of those is collection. And the other one is map. You can think of these as interfaces. Actually, they are interfaces. We have a collection interface and a map interface. But the map interface gets a little more complicated than the interfaces like we've seen. So it seems like something more when we get to it, but for now, think of it as the interface like we saw. the rules on how things connect, which you can use the analogy of physical plugs, like the USB plug. The rules of how we connect devices together are the shape of the USB plugs. They're standardized. So we set up those rules as the interface. Collection has set, list, stacks, queues, priority queues. We'll probably look at those. A priority queue is a queue, except that instead of first in, first out, it organizes the data to its natural order. So if we pass in a bunch of strings, they will be switched to alphabetical order and go through an alphabetical order. If we pass in a bunch of numbers, they'll be put in sequence and then routed out. So remember a couple weeks ago when we looked at interfaces, one of them was the comparable interface, and we had that compare to method. So priority queues would require that things have the compare to method, so that way we can tell which one is bigger or smaller than the other, so they have a natural ordering to it. And more. Most of those are child classes of vectors. We might look at vector too. Maps, we have hash maps, tree maps, a whole bunch of them. They all have map in the name. We won't see very many maps. We'll see a couple. You've encountered one type of map, of course. Everybody's in the dictionary. Like they're very popular in Python. Key value pairs, and we have some sort of string that is the key, and that way, might also call them associative arrays, depending on the language. But as we use a string instead of a numerical index for an array, basically, is one way to think about it, or a way to introduce it. Dictionary is a very special type where our key is a string. It's a type of map. We can use anything we want as the key. It's rare to use anything other than strings because that just makes sense to the human mind. But we can use whatever we want. If we have a bunch of animal objects, we could use those animals as the key. So maybe that animal object, the weight field from the animal objects is the key to some of the class, the key to the people class, where we have name, age, and town or something. We can use whatever we want as the key and the value, and that's what a map is. And then the different types we have in Java are how those are put together. So we could set them up as hashes. We could find them as trees. It's parallel stuff. There's lots and lots of them. We'll pick quite a few. I even noted in these yellow pages to on page 778 in your textbook is a UML, the collections interface. Maybe glance at that to see what methods you have in all of this stuff. Things like that. Let's look at some of these that we have, but that brings us up to about 5 after. I was looking for 5 after to jump in and start using the ones, looking at these that are built into the language. Stacks and queues are going to be very important for us. Some terminology that will go with those. We can talk about that as we type a trivial example of it. 10 minutes sound good to everybody? Take a break. Get affirmative stuff here in the classroom. So I assume that's okay from those on the Zoom call. So my laptop says 7:03. Let's take 10 minutes. We'll get back to it at 7:13. See y'all in just a moment, and then we'll actually do some stuff there.